Hello. We are going to tackle some logarithmic functions today, which follows really nicely. Our last topic was our exponential functions, and this is a really natural lead in here. So what are we going to get into in this video? We're going to talk about being able to take an equation that is in logarithmic form and convert it into exponential, and vice versa. We're going to take an expression that's in exponential form and convert it to logarithmic. We've always talked about this being like two languages, converting something from English to Spanish and vice versa. And at the end of the day, we're going to be talking a lot about equivalence. These, we've got two expressions that are equivalent, just one's in logarithmic form and one's in exponential form. So we've got a lot of verbiage here today, and feel free to paraphrase this in your notes in a way that makes sense to you. So what are the origins of a logarithmic function? Where did they come from? Why do we even need to bother with them? So we're going to kind of introduce you to this idea of an exponential function being a one-to-one function. So here it goes. All right, so we've got an exponential function not only passes the vertical line test, which makes them a function, but it also passes the horizontal line test. In other words, there's no horizontal line that we can draw that intersects the graph more than once. This means if you pass both that vertical and the horizontal line test, your exponential function is considered a one-to-one function. That's a really special designation. Like, that's a really big badge of honor for these exponential functions. At the end of the day, what that tells us is, I'm going to switch to the highlighter now because this is really important. The inverse function of the exponential function with a base of b is called the logarithmic function with a base of b. So at the end of the day, this is what you're going to hear over and over and over again. The log function is the inverse of the exponential function. Now, as soon as we mention this idea of an inverse, the first thing that pops into your mind is this idea of interchanging or swapping the x and the y. So if you start with the exponential function y equals b to the x, the inverse is naturally going to be x equals b to the y. But there's a problem with that. We want to be able to solve this expression or this equation right here for y. That's our big goal. So logarithms give us a way to express this inverse function for y in terms of x. That's what these logarithms do. That's why we had to create these logarithms. So some other helpful reminders about inverses here that you can kind of, again, paraphrase here. So only one-to-one functions have inverses that are also functions. If a function is one-to-one, its inverse can be found by interchanging x and y, just like we talked about. Here's one of my favorites here, part 3, that says, okay, if f of a equals b, then f inverse of b is equal to a. And that's one that'll play a big role down the road for us. Here's one that you may remember from a couple of weeks ago. We were talking about the composition of functions, and we said if we compose these, if we said, let's do f of f inverse of x, the final output is just x. And I want to pause right there, and let's talk about that for a second. So think of x as your starting point. You start with this x value. And then f inverse is going to change it, right? It's going to alter it. However, f is going to step in and undo whatever f inverse did to that x. And at the end of the day, you're right back to where you started with x. And that composition can go either way. We could start with x, perform f, and then perform f inverse, and you'll still get your x. And then another thing that will come back at the end of the video is that the graph of f inverse is simply the reflection of f about the line y equals x. So really today is going to revolve around, we've got this exponential function that increases and is concave up, and the inverse is going to be this logarithmic function that also increases but now is concave down. So good job hanging in there so far. We're throwing a lot of theoretical stuff at you, a lot of definition type stuff at you, and we're going to just finish up right here. So, and every piece of a definition is important. That's what I want to try to that's what I want to try to impart upon you, is that every little thing, even if it seems like it's really significant, is probably more important than we think it is. So for instance, we're saying all the x's have to be positive, all the b values have to be positive, and b cannot equal 1. So b, what are the options for b? B could fall between 0 and 1, or b could be greater than 1. Those are the options. So if you have this expression that we were battling with there a second ago, this is the inverse of the exponential. It's equivalent to this log equation right here. And so the function f of x equals log base b of x. Notice how we pronounce that. It's pronounced log base b of x. It's the logarithmic function with a base of b. So I think what we're going to find out here is converting from logarithmic to exponential is really easy for me, but reversing that and converting it from exponential to logarithmic is a little more challenging. And so we're going to try to develop some tools for that. So first of all, how do we convert a logarithmic form or convert from logarithmic form to the more familiar, more comfortable exponential form? And this is where we use a technique called around the world. So I start with my base, and he is going to be raised to the y power, and that's going to be equal to x, okay? So we could say b raised to the y equals x, and these two equations are equivalent. Bada bing, bada boom, equivalent. Now, something you'll see down the road is we like to say that logarithms, this logarithmic expression, is the exponent. So you'll notice when you rewrote it, the exponent was y. So logarithms are always equal to the exponent. Whatever they're set equal to is going to be your exponent there once you convert it. And we are going to try to go back and forth between these two forms. So again, I think we're going to start off with a little easier one. We're going to go around the world. Okay. And I guess that's the one thing, if you want to make a note here, when we go from logarithmic to exponential, I'm going to use around the world. So this is our Q. All right. So we'll say 5 raised to the second power equals x. 5 raised to the second equals x. Let's see. B raised to the third power equals 64. B raised to the third equals 64. How easy is this, huh? How easy is this? Okay. 3 raised to the y power. So the only thing I got a little tricky is I put, instead of putting like the y equals over on this side, I just put it on the other side. And that's going to equal 7. So 3 raised to the y equals 7. If I had written the original problem as y equals log base 3 of 7, I would have got the same thing, right? 3 raised to the y equals 7. All right. So now we're just flipping the script and we're going from exponential to logarithmic. And one thing I'd like to do is kind of put these two statements side by side. So if I have b raised to the x equals, actually, let's just tweak this. Let's just say, to keep it consistent, we'll say b to the y equals x. Okay, that's going to be equivalent to log base b of x equals y. So a couple of things we could highlight here. So when you're in exponential form, this is called your base, right? You have a base value of b being raised to the y. Well, we also have similar terminology here when you have your logs. This b value is called your base. So although it's kind of a different print size, those are both called bases. And then the other thing that I like to see is this exponent that you have in exponential is always what you set your log to when you write these expressions. So let's try to put all that together here. So 12 is your base. So I've got log base 12 of x, and I got to set it equal to my exponent, right? So that's all there is to it. Now, if you ever have any doubts, and I think you're like, yeah, I think I did it right, I'm not sure, what you could do is take this expression right here, okay, and go around the world. And you could say, okay, 12 raised to the second equals x. Yep, boom, it checks out perfect. So that's my best advice when you're converting exponential to log, is you can always, check your work by doing around the world. Who's your base value? It's a b. So we'll go log base b. So you got that really nice handwriting with a little subscript of 27. And again, if you want to put parentheses around the 27, I haven't mentioned that yet, but that's always a cool thing to do. And you set it equal to your exponent, right? In this case is a 3. All right, who's your base value? Your base is e, right? So we'll say log base e. That e represents Euler's number. It's a constant, 2.718, and but that's not a real big deal for today. Of 33, and you want to set that equal to your exponent, right? All right. So the last thing I want to get into today is just a real quick discussion about graphing a log function. And the whole theme today is that logs are the inverses of your exponential functions, right? So let's see if we can build on that idea. So let's imagine that we have this exponential function, f of x equals 2 to the x, right? And we've seen in a previous video how we could make a table of values and graph 2 to the x. Well, all we have to do to graph the inverse, which is going to be log base 2 of x, is switch those rows, okay? So basically, all of these x values are going to slide into this row right here. So we could write -2, -1, 0, 1, 2, 3, and then vice versa. Whoops, maybe we'll try this one. All of these bears here are going to slide into this row. Basically, all your x's became y values, and all your y values are becoming x values. So now you've got, let's see, you've got your 1/4 here, your 1/2 here, your 1, your 2, your 4, your 8. And when you go to plot those points, you're going to end up with a graph similar to this, okay, where this red graph right here, this red graph represents your log graph from plotting all the points that we just rewrote in that second table. Now, there's a lot of other characteristics that we'll get into down the road. A couple of big ones are your x-intercept is going to be a 1. Okay, your graph is also asymptotic to the y-axis. So let's see if we can add that in there. We'll try to do this in red so it jumps out. So you've got this vertical asymptote right here where the graph is approaching the y-axis, but technically never does touch it. And then the graph just continues to grow and increase without bound. So anyway, that's a quick recap of converting from logarithmic to exponential and vice versa. Hope you feel pretty good about it. We're going to get a little more practice under our belt and really be awesome at this. Have a good one.